Our first planner speaker is Professor Rafael Klotz from University of Manitoba, and he's going to talk about Henkin and analytic functional on C-star algebras. Rafael, please.
Thank you, Javad, and thank you very much to the organizers for inviting me to speak in this nice conference. Let me start by saying that, is this working? Yes, that all of this is based on joint work with my former postdoc, Edward Timko. Okay, so my title was about Henkin and analytic functionals on C-star algebras. I'm going to spend quite a bit of time motivating what these objects are and why they're interesting. And to do this, I would like to discuss a operator theory problem related to the functional calculus. Okay, so let's take H to be a separable Hilbert space and T to be a contraction on it. Then a consequence of von Neumann's inequality is this: is you can define a map that takes a function f from the disk algebra and associates to it the operator f of t, and that turns out to be a completely contractive homomorphism. Okay, so here the disk algebra A of D, this is the algebra of continuous functions on the closed disk that are holomorphic on the interior. Okay, so that's a basic fact. This is what I will refer to as the usual functional calculus, and we've heard about this a little bit in Michael Jury's talk before this one. And the basic question I would like to address is this. So you might want to enrich the domain of this map, of this functional calculus, to a bigger algebra than the disk algebra. And the reason is that, the bigger the algebra, somehow the more information you have, the more function theoretic information you have to study your operator. And for me, the target algebra will be H infinity. So what I would like to do is take this map and extend its domain to the entire algebra H infinity of the disk. So the algebra of all bounded holomorphic functions on the disk. Not only that, but because H infinity has the special feature that it has a weak star topology, you might want the extension to respect this weak star topology. Okay, so what I would really like to do here is determine when it is possible to extend this functional calculus to a weak star continuous homomorphism defined on H infinity. Okay, so what I would like to achieve here is item 1 in this lemma. I would like to know when it is possible to extend the functional calculus to a weak star continuous homomorphism from H infinity into B of H. And let me clarify maybe quickly here what I mean by weak star continuous. So here's the setup here. We have the disk algebra. I view this as sitting inside continuous functions on the unit circle by looking at boundary values, or just a restriction to the circle. And in turn, continuous functions of the circle, I view this as sitting inside L infinity of the circle with respect to arc length measure. And I also view H infinity as sitting inside of this L infinity via boundary values. Okay, now H infinity inside of L infinity, this is a weak star closed subalgebra, so it inherits the weak star topology of L infinity. And this is what I'm referring to here when I say weak star continuous. Okay, so once again, the basic problem I'm trying to address here is when it is possible to achieve item 1, and it's not too difficult to show that item 1 is equivalent to the following property: that whenever you have a bounded sequence Fn in the disk algebra, which converges pointwise to 0 on the open disk, then the corresponding sequence of operators Fn of t converges to 0 in the weak operator topology. So this kind of condition, this will occur many times throughout my talk. So let me right away give you some kind of reason why this condition is meaningful. So what does it mean for a bounded sequence, for a sequence to converge boundedly pointwise to 0 on the open disk? This is exactly equivalent to the sequence converging to 0 in the weak star topology of H infinity. Okay, so roughly speaking, what this lemma is saying is this: if you want to guarantee that you can extend your functional calculus to weak star continuously, what you have to do is make sure that it is as weak star continuous as you can conceivably ask of it. Okay, this is really what item 2 is saying. It's saying that as far as only the disk algebra is concerned, you have some form of hidden weak star continuity. Okay, so that's kind of a reformulation of the property that I'm really after here. And now let's see what we can do with this. So first thing I want to point out here is that there's a classical theorem of Nagy and Foyash that says that these properties are in fact automatic if you start with a contraction which is completely non-unitary. Okay, which means that there is no unitary summand inside of T, if you want. Okay, so that's one fact, and there's another well-known fact that starting with a general contraction T, you can always write it as a direct sum of two pieces, one of which is completely non-unitary, and the other one is a unitary operator. Now, the question that I'm addressing here, that of the existence of this weak star continuous H infinity functional calculus, this splits into two questions, one for each summand here. And the completely non-unitary summand, we don't have to worry about it. It's things hold automatically there by the Nagy-Fourier result. So really the entire problem here reduces to the corresponding question for the unitary operator U. But for U, you actually have a spectral measures to help you here. So you can try to study this question for U in terms of its spectral measure. If you look at item 2 here, this is really saying something about the spectral measure of U. So this entire problem for a general contraction T reduces to one about measures on the unit circle. Okay, so let's do that. This now becomes a measure theory problem. So let's look at this from the measure theoretic point of view. So let's take mu to be a regular Borel measure on the circle. I would like to define two properties of a measure here. The first one is that of being analytic. So we said that the measure is analytic if it annihilates the disk algebra. Okay, in this sense, that if you integrate anything from the disk algebra against mu, you always get 0. And the other property, and that is really the crucial one for my talk, is that of being Henkin. So I'm going to say that the measure mu is Henkin for the disk algebra if it has a familiar looking property. So if whenever you have a bounded sequence in the disk algebra converging to 0 pointwise on the disk, then the corresponding sequence of integrals converges to 0 as well. Okay, so if you think back on the previous slide, the characterization that I gave of the class of contractions that I'm after in terms of the functional calculus, and if you think that you have a unitary, then really what you're left to do here is try to determine when the spectral measure of a unitary operator has this special property of being Henkin. Okay, so what you really want to do is understand which measures on the circle are Henkin. Unfortunately, quite a bit of information is known about such measures, which I would like to summarize in the following theorem. So this is mostly due to Henkin and Valsky. Okay, there's two assertions here. The first one is genuinely a combination of work of these two people, and it says this. It says that a measure is Henkin if and only if it is absolutely continuous with respect to some analytic measure. Now, this is not the typical way in which this is stated, this theorem, but it's true. Okay, so this is a consequence of these of theorems of Henkin and of Valsky. I'm not going to tell you precisely what these theorems are at this point. I will come back to it in a few minutes, at which point I will be a bit more explicit. Okay, so you could say, well, there you go. This is the answer to your operator theoretic question. If you want to determine whether or not your contraction admits a nice functional calculus, you have to look at the unitary part of that contraction, look at the spectral measure, and you have to make sure that it's absolutely continuous with respect to some analytic measure. Now, this may not be entirely satisfactory, right? Because it seems that you're just moving the problem around. Now you're left to try to understand what an analytic measure is. But there's a bit of a miracle that occurs at this point, which I would like to call the FNM-Rees miracle. And it turns out that actually this is quite a big restriction. Okay, so if you combine this Henkin and Valsky statement to the classical FNM-Rees theorem about analytic measures, you get a more familiar statement, perhaps, which says that a measure is Henkin if and only if it is absolutely continuous with respect to arc length measure on the circle. Okay, so why do I make a big deal out of this? Why do I color this rainbow? Why do I call this a miracle? It is because this is really special to the one variable case. Okay, and this is a bit of a foreshadowing for the rest of my talk. So the first of these two statements here, we will see in various forms throughout my talk in greater and greater generality, whereas the second one is kind of special. Okay, we will typically, you should not expect miracles to occur all that often. So this, as you will see, is kind of special to this setting. All right, and then you can say, well, I have really solved the operator theory question. So here's the corollary that answers the question. If you have a contraction on a separable Hilbert space, then it admits a weak star continuous H infinity functional calculus if and only if the spectral measure of its unitary part is absolutely continuous with respect to arc length. And by the way, this kind of explains the terminology. So a kind of a standard terminology for the class of contractions with a nice functional calculus like this is that you call them absolutely continuous. And this corollary justifies the terminology, right? It is because that is the criterion. All right. So this is the story in one variable. Now, what I would like to do next is take this story into the multivariate world. So here I have the disk algebra. Why don't we look at the ball algebra instead? Okay, so we'll take some positive integer d, at least 2. B sub d will be the open unit ball in the complex space in dimension d. S sub d will be the boundary, the unit sphere. Sigma sub d will be surface measure on the sphere. And as I said, I replaced the disk algebra by the ball algebra, A of the ball. So that's the algebra of all continuous functions of the closed ball that are holomorphic on the interior. As before, I view this as sitting inside of continuous functions on the unit sphere, okay, by restricting to the sphere and using the maximum modulus principle if you want. And in turn, this algebra of continuous functions I view as sitting inside of L infinity of the sphere with respect to surface measure. And our old friend H infinity is still there. So H infinity of the ball this time is the algebra of all bounded holomorphic functions on the open ball, which we view as sitting inside of L infinity again. Okay, so this, these are analogs of the previous object. So you can make similar looking definitions here. So here they are. Instead of a measure on the circle, now you have a measure on the sphere. I'm going to say that it's analytic if it annihilates everything in the ball algebra. And I'm going to say that the measure is Henkin for the ball algebra if, again, it has this familiar looking property by now. So if whenever you have a sequence Fn bounded in the ball algebra, which converges pointwise to 0 on the open ball, then the corresponding sequence of integrals converges to 0. Here again, this property, the property of or bounded pointwise convergence on the open ball, this is equivalent to weak star convergence to 0 in H infinity. Okay, so this is the kind of the reasoning or the meaning of this condition. Okay, so you can make these definitions, and now, of course, you can ask yourself, can I say anything about the nature of Henkin measures in this multivariate setting? And as it turns out, you can. Much of the theory I alluded to earlier works in this more general or this multivariate context. So let me be a bit more precise than I was previously. So I told you before that there were two crucial tools, one due to Henkin, one due to Valsky. So let me spell out what these are. So this is first the theorem of Valsky. This is sometimes called the Valsky decomposition. And it says that a measure mu is Henkin if and only if it is of a very special form, if it is of the form analytic measure plus something absolutely continuous with respect to surface measure. All right. Now, I want to mention something here that there's another way of kind of viewing this statement, which makes it not too difficult to prove. What this is saying is equivalent to the following. Take the measure mu, okay, and consider the corresponding integration functional on the ball algebra. Okay, so what Valsky is saying is that having a Henkin measure is equivalent to the fact that your integration functional on the ball algebra can be extended weak star continuously to L infinity. Okay, and that is really equivalent to what is written. All right, so that's the Valsky decomposition, the Valsky theorem. Now, what was the Henkin part of the story? It says this: the set of Henkin measures for the ball algebra forms a band of measures. Okay, a band of measures is simply a collection of measures which is closed under absolute continuity. So if you have two measures, mu and nu, you know that mu is Henkin, you know that nu is absolutely continuous with respect to mu, then that forces mu to be Henkin as well. All right, and once you know this, you can give a similar sounding characterization of Henkin measures to what we had for in the one variable case. So here's, oops, okay. Here's a corollary. A measure is Henkin for the ball algebra if and only if, now this will look a bit complicated, so I will explain in a second. So if and only if it is absolutely continuous with respect to a convex combination of total variations of analytic measures. Okay, so this is a bit more complicated than what we had when d is equal to 1, but I'd like to convince you in a few minutes that this is kind of the same thing. Okay, and first let me explain how this works. Okay, so let's look at the proof. So how do you go from right to left? Okay, then I claim this is really a consequence of two things: of Henkin's theorem, that the Henkin property is preserved under absolute continuity, and the trivial fact that analytic measures are Henkin. Okay, so if you start with an analytic measure, then it does nothing on the ball algebra. It's just 0. So clearly that's Henkin. This is the triviality. Now you apply Henkin's theorem, and that implies that the total variation of an analytic measure is Henkin as well. So if you take a convex combination of these things, you remain a Henkin. And by Henkin's theorem again, you can also pass to something that's absolutely continuous with respect to such a thing. Okay, so this is how you go from right to left. And from left to right, so you assume that you have some Henkin measure, then you apply Valsky's theorem, and you realize that what you have to do here is prove the conclusion either for an analytic measure or for something that's absolutely continuous with respect to surface measure. For analytic measure, again, this is a triviality. So you're really left here with dealing with surface area measure, sigma d. And this you can just do by hand. Okay, so you just take sigma d multiplied by the kth variable. Okay, zk times sigma. This becomes an analytic measure. This is a consequence of Cauchy's formula on the sphere. And moreover, when you and then when you take the total variation of this, you just get the modulus of zk. And when you take this convex combination here, what you get is something that's comparable to the measure sigma. Okay, so this is how the proof goes. All right. But now, okay, so this looks a bit like what we had for in the first statement in one variable, right? You have some kind of description of Henkin measures, but again, it might not be completely satisfactory in your eyes because it's not completely clear what analytic measures should be. In one variable, this was resolved through the F&M-Rees miracle. So then you wonder, is there a miracle that occurs here as well? And well, there is no perfect analogy with a perfect analog of the F&M-Rees theorem here, of course, right? Because it's not true that an analytic measure must be absolutely continuous with respect to surface area measure, simply because you can take, for instance, a big circle around the origin, multiply by a variable, and then by the one variable, say Cauchy formula, you'll get some analytic measure, which is clearly not absolutely continuous with respect to sigma. So there's no perfect analogy with the F&M-Rees theorem here. So you can't expect such a clean statement as what we had in one variable, but still there is another miracle here, a bit more complicated, but that still gives you a better description than what I currently have told you about. And that involves the idea of representing measures. So let me denote by R0 the set of states on continuous functions on the sphere, or equivalently the set of probability measures, with the property that when you look at their how it acts on the ball algebra, well, it simply reproduces the evaluation at the origin. Okay, so if you integrate something in the ball algebra against the measure mu, you just return the value of the function at the origin. And at this point, I'd like to point out the fact here that it is a consequence of the classical F&M-Rees theorem on analytic measures that when d is equal to 1, there's only one candidate in this set, and that is arc length measure. Okay, so this already hints at the fact that perhaps the right way of stating things in several variables is not, you shouldn't expect to have something with respect to arc length measure anymore. Maybe you should expect something that involves the set R0 instead. And that is indeed what will occur. Before I tell you the results, let me just make up some notation here. So by AC of R0, I will denote the set of all those measures that are absolutely continuous with respect to some element inside of R0. Okay, so typically there are more than one measure in several variables inside of R0. And AC of R0 denotes those things that are absolutely continuous with respect to one of the elements in R0. And now here's the classical description of Henkin measures for the ball algebra. This is the classical Coloranga theorem. And it says that a measure is Henkin for the ball algebra if and only if it is absolutely continuous with respect to R0. Now, what is this business here? Why is there another name? Why is it colored in rainbow again? I don't want to go through the details of the proof of the Coloranga theorem here, but let me just say that this fact of Forelli here is kind of the replacement for the F&M-Rees miracle. Okay, so there's one way to prove the Coloranga theorem is at some point you need some kind of approximation theorem, and this was proved by Forelli. So I'm not going to tell you what that is. I just want to point out that once again there is a bit of a miracle here, which somehow there's several pieces of this puzzle that have to come together to prove the Coloranga theorem. Several of these pieces we will be able to reproduce in the more general context that I'm after today, but this one piece here, due to Forelli, this is the one piece that will be missing. Okay. Anyway, so this is just a side comment. Okay, and now, well, you can see that this basically solves the question of, well, what is a Henkin measure for the ball algebra? It is a pretty concrete description of what these things are. So, okay, but now let's take a step back. Why should you even care about Henkin measures? Well, I tried to convince you that in one variable you should care because this allows you to identify those contractions that admit a nice functional calculus. So now you have this multivariate version. So you might hope that this is telling you something about the functional calculus in several variables. So let's analyze this question. So let me go back to operator theory here. But this time I would like to look at multivariate operator theory. So we have a separable Hilbert space H. We have a bunch of operators on it that commute with one another, T1, T2 up to TT. And I want to assume that you have a row contraction here. So Michael Jury described this property a bit earlier. So let me just repeat here. So the condition, so being a row contraction means this: you take all of these operators, you package them into a row, you view the row as a operator from D copies of H into 1 copies of H, and you ask that this be a contractive operator. Equivalently, this is just asking that this inequality here be satisfied. Okay, now it is well understood nowadays that well, okay, so in one variable, you had the contraction, and then there was some kind of this algebra of functions that give you a functional calculus was the disk algebra. So here, your naive guess initially might be that the functional calculus here will involve something like the ball algebra, but it's well understood nowadays that this is not the right algebra for the job. You have to do something else here, and what you have to do is look at algebras of functions on the Drury-Arvidsson space. So let me denote by MD the multiplier algebra of the Drury-Arvidsson space on the open-unit ball. I'm not going to say much about this space, okay? There's an entire week, next week, dedicated to this whole thing. Michael Hartz will give a mini course or mini lecture series about this. So if you've never seen this, I really encourage you to attend. So let me be very brief. I will just say this. So the Drury-Arvidsson space is a reproducing kernel Hilbert space on the ball, consisting of holomorphic functions. And yeah, so attend the meeting next week to learn more about it. But it has a multiplier algebra, which I did not by MD, okay? And intuitively, you should think of this as a replacement or an analog of the algebra H infinity, all right? Now, it's a fact that this multiplier algebra contains the polynomial. So if you want, you can take the norm closure of the polynomials inside of MD, and that I will denote by A sub D, okay? And this is a rough analog of what the ball algebra was. Okay, and I really mean this is an analogy here. You should not, you should not think that these are the same kind of algebra. So there is a relationship between AD and the ball algebra in the form of this inequality here. That if you take a function f in AD and you take its norm inside of and take its norm, then this always dominates the soup norm over the ball. Okay, so the norm in the ball algebra. However, this inequality is strict in general. Okay, so this is not, so the two norms are different here. The algebra AD and the ball algebra are different algebras. And one consequence of this inequality being strict is that AD is not a uniform algebra. Okay, it does not live inside of a commutative C-star algebra. It does not live inside of continuous functions on some compact Hausdorff space. And this is a bit confusing because, I've been telling you about measures all along. And now, why was I talking about measures? Well, that's because measures are the elements in the dual space of continuous functions on the sphere, for instance. But now I'm telling you that, well, there's no continuous functions here. So then you might ask yourself, okay, so what's the replacement for this? What's the replacement for continuous functions in the sphere? And here's one kind of a cheap way of getting out of this problem. Let's just take whatever AD is, okay, as a set of bounded operators on the Drury-Arvidsson space, and let's just generate a C-star algebra out of this. I'll call this T sub D. Okay, so this is, if you want, the replacement for continuous functions in the sphere. Unfortunately, it has some flaws or some quirks. It is highly non-commutative in a way because it contains the entire ideal of compact operators, but not all commutativity is lost. Okay, there are still some remnants here. So if you mod out the ideal of compact operators inside of the C-star algebra TD, then you recover continuous functions on the sphere. Okay, so this is kind of a funny C-star algebra. In a way, it's non-commutative. It makes it kind of harder to study, but there is kind of a remnant of commutativity here. And in particular, whereas we were looking at measures before, we can't just be looking at measures anymore, okay? So the dual space of the C-star algebra will not consist entirely of measures. The measures on this sphere will still be in a dual space. That's because you have this commutative quotient here, but typically there are, well, not typically, you have more things than that in general. Okay, now if this is the first time that you hear about these objects, at this point you might be wondering why would you want to study these hideous beasts? I mean, they look so annoying compared to my lovely ball algebra. So why would you want to do this? And the answer is that you don't really have a choice. And not only do you not have a choice, but they actually do the job that you really want them to do. Okay, so this is an observation that Arvidsson made, that this algebra AD is precisely the gadget that you need to recover a functional calculus. So Arvidsson proved that you can define a map that takes a function f in AD and associates to it an operator. Okay, f evaluated at the commuting row contraction, and this will give you a completely contractive homomorphism. Okay, so this is kind of the replacement for the very first thing I said today, which was, von Neumann's inequality gives you this functional calculus defined on the disk algebra. Now we have something a bit different. Okay, the disk algebra has become this other algebra AD. But now, once you know this, you can ask the same question that I raised previously. Okay, so what I wanted to do was kind of enrich the domain of the functional calculus so that I could use, I could use a richer space of functions to try and study my operators. And you can ask something similar here. So what the target here will be to extend the domain of this functional calculus from AD all the way up to MD, which is a bigger thing. All right, and once again, although I haven't made this clear here, MD does have a weak star topology, so you might want this extension to preserve the weak star topology. Okay, so now we're back to what we were doing with one operator. Okay, what we're trying to do is this. So we have this commuting row contraction T, and we're trying to figure out when item 1 in this lemma holds. When is it possible to take the functional calculus and extend it in a weak star continuous way all the way to MD? Okay. And I should clarify here again, so what's the weak star topology? Well, I view AD inside of MD as sitting inside of the bounded operators on the Drury-Arvison space. MD is then the weak star closed subalgebra, so it inherits the weak star topology from the B of H. All right. And then a very similar argument to what you have to do in the one variable case gives you kind of a characterization of when this occurs. Okay, so it's roughly speaking the same intuition. So you can extend your functional calculus in the way that you want. Precisely when your functional calculus is as weak star continuous as you can conceivably ask of it, okay, as far as the algebra AD is concerned. So the condition is that whenever you have a bounded sequence Fn in AD, which converges pointwise to 0 in the open ball, then the corresponding sequence of integrals converges to 0 in the weak operator topology. And in this setting as well, bounded pointwise convergence to 0 on the ball, this is the same thing as weak star convergence to 0 in MD. Okay, so now what did we do next in one variable? I pointed out that there was this classical fact of Nagy and Foyash that when d is equal to 1, said that when you have a completely non-unitary object, this property holds automatically. That is still true. Okay, this is something that we proved several years ago with Ken Davidson. So if you assume that your commuting row contraction is completely non-unitary, then these conditions automatically hold. All right, and moreover, it's also true in this setting that you can take your commuting row contraction and you can split it as a direct sum of two pieces, one of which is completely non-unitary. Okay, so it's handled by the previous point, and the other one is unitary. So we have to be a bit careful what you mean by unitary here. What I really mean is that you have a spherical unitary. You have a commuting d tuple of normal operators u1, u2 up to ud, whose joint spectrum is contained in the sphere. Okay, so it's not so easy to track down a reference for this, but this was at the time where we were working on this. This was communicated to us to me and Ken Davidson by Jörg Eschmeyer. Okay, so if you put all of this together once more, the functional calculus question for commuting row contractions reduces to one about measures. That is because this spherical unitary guy does have a spectral measure. Okay, so this once again reduces to a question about measures on the sphere. What kind of measures? Well, a Henkin measure again, but so you might think that I'm just repeating at this point, but there is a bit of a subtlety here, which I will point out in a minute. Okay, so you have a regular Borel measure mu on the sphere. I'm going to set it as Henkin for AD. If at this point this condition looks very familiar now, you have a bounded sequence in AD converging pointwise to 0 on the ball, then you require that the corresponding sequence of integrals converges to 0 as well. Okay, so this makes sense. I mean, I have this algebra AD. I have a spectral measure on the sphere. Then this is the condition that I need according to the previous lemma. So our job now, if you want to understand those commuting row contractions for which I can extend the functional calculus, is to understand what such a measure is. One thing to note here, however, is that I pointed out before that why do we deal with measures? Classically, it's because the C-star algebra is continuous functions on the sphere, and the measures are exactly the things in the dual space. But now I also told you that the C-star algebra here is not commutative anymore. So, there's more things than measures in the dual space. So why just discuss measures? In fact, in this situation, why not make this definition instead. Take some bounded linear functional phi on the C-star algebra TD, and then call it Henkin if whenever you have a bounded sequence Fn in AD that converges to 0 pointwise, then the corresponding sequence of numbers that you get by evaluating phi converges to 0 as well. Okay, so these are similar looking definitions, but in the setting of AD, perhaps the second one makes more sense, right? Because you have more things than measures in the dual space. But at any rate, and as far as the function or the operator theory question is concerned, only the first you only need to worry about measures in principle. So as I was saying, the question now is what does the Henkin measure look like? And why is this different than what I told you about for the ball algebra? It is because of this this algebra AD here. Notice what is the condition in the definition here? It is that on the sequence, it is that it's bounded in AD, right? In the norm of AD. And the norm of AD is not the same as the norm on the ball algebra. So that in principle looks like a different kind of object than a Henkin measure for the ball algebra. With that being said, there is kind of a relationship between these things. So it is a fact that if you have a Henkin measure for the ball algebra, automatically it's a Henkin measure for AD. Okay, that is simply a consequence or reflection of the fact that the norm on AD dominates the norm on the ball algebra. And then wouldn't it be nice if these objects were the same, if these classes were the same? Because if these were the same, then you could just leverage or exploit the known theory for the ball algebra and then answer your operator theory question and call it a day. So wouldn't it be nice if the converse were true? And so is this true or not? And this is a question that Ken Davidson and I worked really, 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 really hard on for a year and a half. It really haunted my dreams for for the greater part of my stay in Waterloo. And we never really figure it out. I mean, we proved a bunch of things related to it, but never could really answer this question. And as far as we could tell, at least we didn't really have a good reason to think that it was not true. So we conjectured that this was the case, and unfortunately we were wrong. So this was proved a few years later by Michael Hartz, who pointed out that these class of measures are indeed distinct. Okay, I will come back at the very end of my talk to tell you precisely what Michael Hartz did here. But for the moment, this tells you that you're in a bit of a bind because you don't really know what this class of measures is, and these are exactly the objects you care about for the functional calculus. All right. So another way of phrasing this is that if you want to understand Henkin measures for AD, you cannot just be looking at the usual Henkin measures for the ball algebra. You cannot just be looking at those things that are absolutely continuous with respect to some representing measure, because this set is strictly contained in the set that you're trying to understand here. So then this leaves us with the following question, which is the central question behind my talk for today. Can you give a description of the set of Henkin functionals for AD? Okay, forget about the measures. What if you want to do the whole thing? What if I want to understand what a Henkin functional is? All right, so this is that's the basic question I would like to address today. And the way I would like to do this is as follows. I'm going to try to adapt the classical approach that was used for the ball algebra. Of course, this is easier said than done, because for the ball algebra, it was really a measure theoretic problem. And here, we're not dealing with measures, as I keep saying, right? We have a non-commutative C-star algebra, TD. So I'm going to try to do this by using non-commutative measure theoretic ideas. And the reason I'm pointing this out here, or I'm highlighting this, is because this is a non-commutative function theory conference. I'm really happy to have been invited, and I would like to get invited again. So I'm trying to convince you that this indeed fits with the theme of the conference. It may not be the same flavor of a non-commutative function theory that Michael Jury has been telling us about, but in my opinion, it is kind of a different perspective on these ideas. Okay, so let me tell you about the general setup then. Okay, this will look quite general, and I promise that when things get very general, I will keep going back to some concrete examples that we've seen already. Okay, so, but the general setup is this: you have some fundamental algebra W, you have a T inside of W, a unital C-star subalgebra, and you have A inside of T, a unital norm-closed, say, subalgebra. So you should think of A as being non-self-adjoint. Typically, these are the examples that we care about the most. So what kind of objects are we after here? We're after something like Henkin measures. So I try to go to the next slide. I don't know if it worked. It seems to be frozen on my side. I don't know if you guys are seeing anything, but I am not. Oh, okay, there we go. Sorry, so the snow is slowing down my internet. Let's just go with that. Okay, so this is the definition here. So we want to be looking at something that looks like a Henkin measure, okay? So I'm going to take a functional defined on the small algebra A. I'm going to call it Henkin relative to W if, as before, it is as weak star continuous as you can ask of it, okay? So if whenever you have a bounded net AI in the algebra A that converges to 0 in the weak star topology of W, then the corresponding sequence of numbers that you get when you apply phi converges to 0. Okay, notice, and then the set of such things I will call denoted by hen sub W of A. So notice it's a bit of an annoyance here. I have to keep track of what W is because you can't talk about weak star topologies or weak star convergence to 0 or something like this if you just look at A, because A may not have a weak star topology. So you have to kind of have this ambient fundamental algebra to make sense of this. Okay, so you have to keep track of what W is. And then what am I after then? So in the classical case, I was after those measures whose restriction to the ball algebra was Henkin in this way. So then what's the replacement here? Well, I replace measures by arbitrary functionals on the C-star algebra. And I want to know which of those have the property that when you restrict them to the small algebra, you get something that's Henkin. Okay, so what I'm really interested in today is try to give a description of this set B. And before going on, I would like to give you a rough idea of what the goal is, okay? The goal theorem. And to do this, I need the following set, which looks a bit strange, so let me explain. So here's what you do. You take those functionals on the C-star algebra T that have norm 1 and that annihilate A. Okay, so if these were measures, I would call this an analytic measure with norm 1. Then you take the absolute value of this functional. I will tell you in a second what that is. And you take the norm closure of the convex hull of these guys. Okay, so you get some norm closed convex set in the dual space of the C-star algebra T, and I call this delta. Now, again, if these were measures, I would be taking the norm closed convex hull of the total variations of the analytic measure at norm 1, right? So you know what the absolute value of a measure is. It's total variation. Now, how do you do? What do you do when you have a general C-star algebra? Well, you can do something similar. It's a bit complicated. I'm not going to write it down on the slide. Let me just say it in words. So you take your functional psi defined on your C-star algebra. You can extend it to a weak star continuous functional on the second dual of T. That's a von Neumann algebra. And for weak star continuous things on von Neumann algebras, you can write a polar decomposition. And this is where this absolute value comes from. Okay, so this is kind of complicated. It's not overly important for the rest of my talk. Just think of this as some kind of non-commutative version of the total variation of a measure. Okay, why is this important? That is because using these symbols, I can reformulate something that we've seen previously. Okay, so recall what the Henkin-Valsky results told us for the ball algebra. Okay, let me say it in words. What it told us is that a measure is Henkin if and only if it is absolutely continuous with respect to a convex combination of total variations of analytic measures. All right. Well, using these symbols that I've introduced, what this is saying is that you have a measure mu as an element of the dual space of continuous functions. It restricts to be Henkin on the ball algebra if and only if there's an element in delta with respect to which it is absolutely continuous. Okay, so I have done nothing here. This is just reformulating the classical theorem that we've seen before using these symbols. And the reason why I'm doing this is because with these notations, I can tell you what my goal is. So the goal is this. The goal is to show that if I give you a functional on T, then it belongs to my set of interest. It restricts to a Henkin functional on A if and only if it is absolutely continuous with respect to something in delta. Okay. Now, at this point, it's not clear that this is a reasonable thing to ask for, but I hope you will agree that this is really a direct analog of this reformulated measure theoretic fact. Okay, now I should, of course, explain what this means here. What does it mean for two functionals to be absolutely continuous with respect to one another? Here's the definition, if my slides allow me to go forward. Oh, there we go. Okay, so here's the definition. So you have phi and psi in the dual of T. You say that phi is absolutely continuous with respect to psi if the following property holds. You take a positive element in the second dual of T on which the absolute value of psi vanishes, then the absolute value of phi must also vanish there. So this may look horrific to you. So let me try to give you intuition here. So what does it mean for two measures to be absolutely continuous with respect to one another, right? You have to look at measurable sets. And when one measure gives you 0, then the other one must give you 0. So now measures are elements in the dual space of continuous functions. Okay. So now how do you connect something in the dual space of continuous functions to measurable sets? Well, here's what you do. You take a measurable set, you associate to it its characteristic function. Okay, so now you have a function. Of course, it may not be continuous. However, a characteristic function always lies in the second dual of the continuous functions. Okay, so this kind of explains how you might get to this definition here. But again, if this looks too ugly for your taste, just ignore it for the rest of the talk. Just think of absolute continuity of functionals as some non-commutative version of the usual measure theoretic notion. Okay. Now, before I tell you the main result, or I need to introduce one bit of a technical condition here. So I will give you the definition, and then I will give you examples to clarify what it says. Okay, so the condition here is about the triple of algebras that we're after. So we have our triple, A inside of T inside of W. I'm going to call this triple analytic if, roughly speaking, the analytic functionals, so those functionals on T that kill A, are sufficient to detect the weak star topology on A. Okay, and the precise definition is this. So you have analyticity if whenever you have a bounded net AI in the algebra, then it must converge to 0 in the weak star topology whenever it converges to 0 as far as all the elements in AC of delta are concerned. Okay, so I admit this is a bit hard to penetrate when the first time you see this. So why don't I just give you 3 examples of interest where this is satisfied? Just look at the time, okay? So first, the classical measure theoretic triple that we've been discussing at the beginning of the talk is analytic. Okay, so if you look at the ball algebra inside of the continuous functions on the sphere, inside of L infinity of the sphere with respect to area measured, then this does satisfy this condition. It's not completely trivial, and it's not completely clear, but it's something that you can just do by hand. Okay, you have measures here, you can write down a bunch of very explicit formulas, and then you can just check that this is true. Okay, so this is one concrete instance where things work out. Here's another one that is of interest to us. If I can go to the next slide, please. Okay, I guess I have to click for some reason. All right. Anyway, so now the Drury-Arvesson triple is also analytic. So AD inside of the C-star algebra that it generates, TD inside of the bounded operators on the Drury-Arvesson space, that is also an analytic triple. And I want to point out that there's kind of a fully non-commutative or a free version of that triple that is also analytic. So if you look at the so-called Popescu non-commutative disk algebra, which I denote by German AD here, inside of its, so this is an algebra of operators that act on the full Fock space over CD. And if you take the C-star algebra it generates in this fashion, then you get another triple, which is analytic. Okay, so the first one is kind of the classical triple that we've been looking all along, and the latter two are kind of non-commutative in a way. And the fact that the latter two are analytic, again, this is not trivial. It's a consequence of some general criteria that we establish in the paper. Let me just say that one of the key points in showing something like this is the fact that these two C-star algebras, they contain all compact operators. Okay, so this is a technical condition. Now let me get to the main result. Okay, the main result goes like this. So let me recall what the setup is one more time. We have this triple, right? We have the von Neumann algebra W that simply is a way to talk about weak star convergence. We have our unital C-star subalgebra T inside of there, and we have A inside of T, a unital normal closed subalgebra. What else did we have? We have this set delta, right, that you construct out of the analytic functionals with norm 1. And then we have our set of interest B, this which we really are trying to understand. We want to understand, we want to kind of give a description of this set B, all those functionals on T that restrict the Henkin on A. Then here's the main result. The main result is that the goal we set out for ourselves is actually can be achieved. Okay, so there are two statements here. First of all is that the triple is analytic if and only if the set B of those functionals that restrict to be Henkin is contained in those functionals that are absolutely continuous with respect to something in delta. And moreover, if you assume analyticity to begin with, then you have equality between these two sets. if and only if you have a left band. Okay, if and only if B is a left band. So I will tell you in a second what that is. But I want to point out that in the presence of analyticity, we have achieved our goal, right? We have described the set B in terms of the set delta, provided that you know something about B being a left band. So what does that mean? So I told you classically a band of measures is a collection of measures closed under absolute continuity. That's the same thing here, okay? So, sorry. A subset B of the dual space of T is called the left band if it is closed under absolute continuity. Now, I say this is a left band and there's no clear indication that there's any left anything here. So what's going on? So there is a kind of a corresponding notion of a right band here, which would look very similar instead, but instead of having this condition that phi is absolutely continuous with respect to beta, I would have that condition, but on the adjoint functionals. That would be called a right band. Okay, another way of understanding why this is a left band is that once you have absolute continuity between these two functionals up to an epsilon, you get some kind of Radon-Nikodym derivative, okay, that appears as multiplication on the left inside of the functional. So this is why there's kind of and because everything's non-commutative here, this matters, right? So this is the notion of a left band. The notion of a right band plays a role in this theory, but I didn't want to make things too complicated. So let me just leave it at that. So it seems that we've achieved our goal, provided that we can make sense of what this condition is. When do you have a left band? So let me go back to these three concrete examples I've been discussing and analyze this condition in that setting. So for the classical measure theoretic triple, the set B indeed is a left band. Okay, so this is simply a reformulation of Henkin's classical theorem. All right. For the Drey-Arvidsson triple, you also have a left band. Okay, something that's not trivial, but it can be verified. And interestingly, for the fully non-commutative version of the Drey-Arvidsson triple, or for the free version of the Drey-Arvidsson triple, you do not have a left band. Okay, the set B is a right band, but it's not a left band. And here you see, I'm writing different names here. So the way we prove this with Ed is by invoking some other work that we've done with my colleague Rob Martin on, and we were wondering to what extent there is a version of the F&M-Rees theorem that holds for this algebra here. Okay, and some of the stuff we discovered in that project made us realize that this set here is not a left band. Okay, so I think it's quite nice here that the fact that this triple is fully non-commutative in a sense, you can really see this reflected in this set. So it's a right band, it's not a left band, which is kind of curious. Okay. So that's the main result. That's mostly what I want to tell you today. I have 3 minutes? Okay, so let me go to my last slide here, and let me just recast this in our case of interest for the purposes of multivariate operator theory. Okay, so if you just reformulate the main result in this concrete case, then because we have an analytic triple and because we have a left band here, we get a clean, very clean statement. For the Drey-Arvidsson triple, you do have this description of the set of functionals that restrict to be Henkin. Okay, it is equal to the set AC of delta. So this is the analog of this kind of theorem of Henkin and Valsky that I've been discussing for the Ball algebra. And then, but at that stage, I told you, well, this is not fully satisfactory because maybe you find that the set of analytic functionals is kind of mysterious, so you don't really understand it very well. You might want something a bit more precise, okay? And for the Ball algebra, this involved this set of representing measures. So you can try to do something similar here. Oops. There we go. So let me denote by R0 the set of states on the C-star algebra, which reproduce evaluation at the origin on AD. And then inspired by the Coloranga theorem, you can ask yourself, is it true that my set B is equal to all those functionals that are absolutely continuous with respect to something in R0? Okay. And the answer to this question is, I don't know. I don't know what the answer is. I suspect, however, that the answer is no, because of Michael Hartz's example, okay? Oh, yes, I should say. So this is true when d is equal to 1, okay? And I want to emphasize that this is not a measure theoretic question anymore, okay? Because now the C-star algebra is non-commutative, okay? So although this looks like this is asking the same thing as Coloranga, this is different. It's not just about measures anymore. Nevertheless, it's true for d is equal to 1. And for d at least 2, I'm not sure. But I suspect the answer should be no because of this theorem that Michael Hartz proved. Okay, and what Michael Hartz proved is that there exists a regular Borel probability measure, mu on the sphere, which is Henkin for AD, but which is not Henkin for the ball algebra, right? This is how we disproved the conjecture that we had made with Ken Davidson. In fact, Michael proved something a bit better, quite a bit better. He proved that you get a Henkin measure for AD, which is very, very, very far from being Henkin for the ball algebra. It's singular with respect to all representing measures for the origin. And then you would think that this does it, right? You would think that you just take this measure mu, you get a state out of it defined on the C-star algebra. It's inside of B because the measure is Henkin for AD. And then does it lie in AC of R0? This looks like a completely stupid question. I mean, I'm telling you mu is singular with respect to everything in R0. And seemingly I'm asking you, does it mean that mu is not in AC of R0? This looks like a tautology, but it's not because, here it's different. You see, you're asking about absolute continuity for functionals, and you have kind of more options there. So I still don't know what the answer to this question is, but I suspect that this is a good place to start looking for an answer. But at the moment, I don't know if even this inclusion is true. Okay, I'm going to stop here. Thank you.
Thanks, Raphael. Let's thank the speaker first. Wonderful talk. Any questions or comments for Raphael?
I have a question.
Please.
Raphael, so
again,
I mean, the reason that we developed this duality theory in the Drury-Arvison space was to get this weak star continuous functional calculus on the multipliers. And, they turns out that if it's completely non-unitary, then in particular, then it does have a weak star continuous linear functional. So for this more abstract setting, I guess you could look at completely contractive representations of your algebra A. Do you have some idea of when those will have an extension to the to this weakly closed algebra?
It's a good question. I haven't thought about this. Yeah, right. So I really haven't thought about this. I mean, it stands to reason, right? I guess so. I mean, using the theory on the Drury-Arvison space, this is kind of how we got this statement for completely non-unitary computing row contractions. It's an interesting question. I really haven't thought about it. I don't want to say something idiotic, so let me leave it at that. But I think it's a good question. Thanks, Ken.
Thank you, Ken. Any further comments or questions? If not, let's thank Raphael again.